Today we are going to discuss about some example on analytic function. First example is example 1. So that the function fz equal to root over modulus of xy is not analytic at the origin although Cauchy Reiman equation are satisfied in the origin. Solution: given fz equal to root over x. We have given the function fz equal to root over mod of xy. Now we have to show it is not analytic at origin. That means the derivative at origin does not exist. We have to show that derivative of fz at the origin does not exist, and we have to show that CR equation satisfied. That is two condition. This is ux equal to by and minus ux equal to bx satisfied at the origin. So compare with the equation fz equal to uxy plus ibxy. Here our uxy is root of a mod of xy and bxy is 0. Now find the partial derivative at origin of u and v both. That is next at origin del u by del x. By definition we will get this limit x tends to 0 u x 0, this is x, minus u 0 0 u 0 0 divided by x. Our u is root over mod of xy. If we put y equal to 0, then the whole u is 0. Therefore, it will be limit x tends to 0. 0 minus, if we put xy equal to 0, then this value will be 0. 0 by x. 0 minus 0 is 0. 0 by anything will be 0. Limit x tends to 0 will be 0. Similarly, del u by del y is equal to limit y tends to 0. Increment is given on the y variable. Then it will be 0 0 divided by 0. So this is equal to limit y tends to 0. Here if I put x equal to 0, the whole u will be 0. 0 minus 0. This is y, not 0. So y equal to, this is y, this is y, and this is equal to my 0. And b is 0, here b is 0, b is 0. So partial differentiation of b with respect to x and y is 0. Since b is constant, so del b by del x is equal to 0, and it is equal to del p by del y. Therefore, CR equation are del u by del x, which is equal to 0, is equal to del p by del y, and minus del u by del y is equal to del p by del x. Hence Cauchy Reiman, hence fz satisfy Cauchy Reiman equation. Hence fz satisfy Cauchy Reiman equation. Cauchy Reiman equation. Reiman equation at the origin. At the origin. Next, derivative of fx at 0, which is equal to limit z tends to 0 f of z minus f of 0 divided by z. Our function here given is mod of square root of modulus of xy, and if we put xy equal to 0, this value will be 0, minus 0 will be by this value, and this by divided by z. Z is my x plus iy. Z is a complex number. Next, taking z tends to 0 along x-axis, along the curve, not x-axis, along the curve y equal to mx, as limit in complex analysis can be obtained along any path, not along the real axis. So we will take this curve y equal to mx. We get limit as z tends to 0. We have this. If we put y equal to mx, then this will be, that is z is my x plus iy, and taking y equal to mx, so z is converted in term of x 1 plus mi. So as z tends to 0, our x tends to 0. So here limit x tends to 0. This will be my root of mod of x mx divided by x plus I mx. Take the formula. The limit x tends to 0, x square root of mod of m divided by x 1 plus I m. X cancel out. Limit is this value. So this is equal to, this implies fx 0 is what? M square root modulus of this 1 plus I m, which depends upon, which is not unique, not a definite finite number, which is not unique, but value depends on m. Value depends on m. Therefore fx 0 does not exist. Hence the function, hence fz is non-derivable at the origin. Next question number example number 2. So that the function fz equal to xy plus iy is continuous everywhere, but is not analytic. Solution. What we have given? we have given function fz equal to xy plus I y. We have to show that it is continuous everywhere, but it is not analytic. So here we are going to solve this one. Fz is my xy plus I y. Comparing with fz equal to u plus iv, we get u equal to xy and v equal to y. Here u is a function of xy and p is a function of y. That means u and p are polynomial function, and polynomial function is continuous at this point, so it is continuous everywhere. U and p are continuous everywhere, and correspondingly this function fz is continuous. So right, since u and p are polynomial function, since u and p are polynomial in x and y, so it is continuous, as polynomial function is continuous, so they are continuous at this point. They are continuous at this point, and consequently u and p are continuous at everywhere. Consequently u and p are continuous everywhere, and hence fz is continuous everywhere. Next, find out to show fz is analytic. This time we will going to find out the partial differentiation of u and p with respect to x and y, and check out whether the Cauchy Reiman equation are satisfied or not. So next, check out Cauchy Reiman equation. So what is u? U is my xy and p is my y. Is it? Yeah, it is. So find out partial derivative of u with respect to x, treating y as constant. This will be y. Again, partial differentiation of u with respect to y, treating x as a constant. Then partial derivative of b with respect to x, treating y as constant, so it is 0, and partial derivative of b with respect to y, treating x as a constant, it is 1. Now check out Cauchy Reiman equation, that is del u by del x is my y, which is not equal to del v by del y, not equal to 1, that is del p by del y, that is del u del x is not equal to del p del y. Now n minus del u del y. What is del u del y? That is minus x, and it is not equal to 0, equal to del p by del x. That is minus del u del y is not equal to del p del x. That means CR equation are not satisfied. We know that CR equation is a necessary equation for a function fz to be analytic. This implies CR, that is Cauchy Reiman equation. CR equation is not satisfied by the function fz. As CR CR equation, Cauchy Reiman equation, CR stand for Cauchy Reiman equation, is not satisfied by the function fz. It is a necessary condition for a function to be analytic. Therefore, fz is not analytic. Is not analytic. With that, I would like to conclude. Remaining will be in the next lecture. Thank you.